Section 4. You'll hear a man giving a lecture on nuclear fusion. First, you have some time to look at questions 31 to 33. Now listen carefully and answer questions 31 to 33.
I'd like to start by thanking so many of you for attending this, my first public lecture at this magnificent university. I'm going to be talking to you today about nuclear fusion. Before I proceed further, I would like to apologize on behalf of some of our newspapers for the sensationalist and hopelessly inaccurate articles that have been published on the subject over the years. I must confess that my own interest in the subject was actually stimulated by an article published more than 50 years ago in a popular Sunday tabloid with the impressive title, "Power from the Sea." Today, most people would probably interpret such a title as an introduction to a discussion on the latest developments in renewable energy sources, such as wave technology or generating electricity from tidal flows. But back then, little, if any, progress had been made in these fields since the invention of the water wheel. As I recall, following coverage of the opening of the world's first commercial nuclear power station, more than 50 years ago now, at Calder Hall in 1956, the article promised that we would have limitless, almost free electricity within 10 years. It claimed that we could do this using an isotope of water, deuterium, from the sea. This would be used in reactors to combine simple molecules of hydrogen to form helium, releasing energy in the process. Of course, this is different from the process of nuclear fission, which today's nuclear reactors use. I wouldn't like to say that the article I read as a boy was totally inaccurate. It's true that the concept of producing energy from nuclear fusion, essentially reproducing the reactions by which our sun and other stars produce energy, depends on fusing atoms of hydrogen, but the timescale suggested was hopelessly wrong. To this day, despite some very embarrassing false claims from scientists who should have known better, we have not been able to produce energy from nuclear fusion in a controllable way. Let me make clear what I mean by this statement, before some journalist in the audience gets hold of the wrong end of the stick. Yes, we have been able to fuse hydrogen atoms to produce helium and a release of energy, but the balance account has always been negative. We've always had to put more energy into the reaction than we've ever succeeded in getting out. We know the theory works, but we still do not know if we can get fusion to work for us and solve the problem of our energy needs.
Before you hear the rest of the talk, you have some time to look at questions 34 to 40. Now listen and answer questions 34 to 40.
Here, I will briefly explain these problems before going on to give you a summary of the innovative ways being tested to overcome them. First of all, we have to try to understand the incredible physical conditions that exist inside a natural nuclear fusion reactor, such as the sun. To start with, we have to create temperatures never experienced on our planet. Indeed, if we had experienced the temperatures required, then our planet would never have formed. We have to generate temperatures of at least 100 million degrees Celsius in a carefully controlled environment before we can even hope to produce a fusion reaction. The problems are immense, but it can be done. Many of you will know that you can put your hand into a very hot oven and not get burnt, provided you do not touch any of the surfaces. I won't go into the reasons for this phenomenon here, but we are applying roughly the same principles in designs for fusion reactors. I think I can promise you that the heat will be confined to a very small area. The other major problem we have to find a solution to is pressure. The pressures in a massive body like the Sun are vast, and this is what brings the hydrogen atoms into such close proximity to one another that they fuse into helium. We may not have to achieve the same pressures in a fusion reactor, but even so, it is a huge technological problem. What, then, makes me hopeful about the future of energy from nuclear fusion? Perhaps surprisingly, it is developments in laser technology. We can now use lasers to control the nuclear fuel pellets so that they remain suspended inside the reactor without touching the sides. Remember that these pellets are quite small, and because they contain atoms of deuterium and tritium, the two isotopic forms of hydrogen that can be used in these reactions, they are quite light. The lasers will also compress the fuel pellet to raise the pressure to that required to initiate the fusion reaction. Another, far more powerful laser will be used to heat the fuel pellet to the temperature required. This laser, if you like, will act as the trigger to start the reaction. Once started, it is hoped that the reaction will produce enough energy to maintain itself, and also that it will produce a surplus in the form of heat that can be used to produce the steam needed to drive turbines in order to generate the electricity the world needs. To give you some idea of how much energy we can produce, it has been calculated that just 1 kilogram of fusion fuel is capable of producing the same amount of energy as 10,000 tons of fossil fuel. I think you would agree that such an objective is worth working towards. I believe, and I am not alone in this, that nuclear fusion could supply the world's energy needs for centuries to come.
That is the end of section 4. You now have half a minute to check your answers.